Hello, math friends. Today we're going to talk about symmetry. And one thing I want you to keep in mind as we do this is I want you to pretend that you are 7 and think about this as a 7-year-old, because if you try to overcomplicate symmetry, you're just going to talk yourself out of the right answer. So pretend for a second that you're 7 and you're folding paper so that you can cut out pretty hearts. All right, so let's talk about symmetry. Line symmetry. A figure has line symmetry if it's mapped onto itself by a reflection over a line. Let's try to make that a little simpler. Something has line symmetry if you can fold it onto itself. Ta-da! Line symmetry explained. Now, a figure has line symmetry if a perpendicular bisector or angle bisector separates the figure into its own mirror image. The line of symmetry is a blank from all the corresponding pairs of points. All right, so before I fill in that blank, let's just talk about this for a second. If I have this isosceles triangle on the left, and I draw in the line that I could fold it over, it would be this line right here. Now, these bullet points reference a perpendicular bisector and an angle bisector. Well, that's because this dotted line is the angle bisector of this angle up at the top, and it is the perpendicular bisector of this side right here. So lines of symmetry are often perpendicular bisectors and angle bisectors. And in fact, you can always find angles or sides that get bisected by the line of symmetry. Okay, so then it says the line of symmetry is blank from all corresponding pairs of points. So corresponding pairs of points would be like this one right here and that one right there. The one on the left, when I fold it, would end up on the one on the right. That makes them corresponding. And this thing here means that those two pieces are congruent. So the line of symmetry is, it's in the middle of the points. And a fancy word for in the middle is equidistant. So the line of symmetry is equidistant from the points. All right, it says in the figures below, sketch all the lines of symmetry. Well, in the first one, there's only one. In the second one, there's this line. That looks pretty good. But in fact, if I tilt my head, couldn't I also fold it this way? Or if I tilted my head again, whoa. If I tilted my head again, it's also this one. There are 3 lines of symmetry in the next one. And then in this rectangle, I could fold it down the middle, okay, the hamburger way, or I could fold it along the long way, the hot dog way, okay? And I wonder if I could fold on the diagonals. No, if I fold on the diagonals, that would not work out. So the diagonals of a rectangle are not lines of symmetry. Does the diagonal technically cut it in half? Well, yeah, but it's not a line of symmetry. And then I got this hexagon over here. Let's see. So if I wanted to fold this hexagon, I could fold it like this, which means if I tilt my head to either direction, kind of like a dog with a loud noise, I could fold it like that. And if I turn my head slightly, not so much, I realize I could fold on these vertices too. These are all fold lines or lines of symmetry for that hexagon. All right, well, I talked about turning my head. That means there might be this other thing called rotational symmetry. So a figure has rotational symmetry when if it's rotated around a center point by less than 360 degrees, the figure appears unchanged. Okay? In other words, think about if you have little nieces or nephews or cousins, or you remember being a baby yourself. Remember those shape sorter things where you have a square block and you got to put it into the hole? You could hold the square one way and drop it in the hole, or you could turn it the other way and drop it in the hole. That has rotational symmetry because you can turn it, but it still looks exactly the same. So let's see. It says the point around which the figure is rotated is called the center of rotation, and the smallest angle needed for the spin is called the angle of rotation. Okay, fine. Find the number of rotated positions in which the object looks exactly the same. That's called the order of rotational symmetry. So in other words, the number of turns you can make is the order. And then to calculate the angle of rotational symmetry, 360 degrees would be a full turn. And if you divide by the order, you get the smallest angle of rotational symmetry. All right, so let's talk about this square here. The order of rotational symmetry for a square means how many different ways can I turn that square and still drop it in a square-shaped hole? Well, I can drop it 4 different ways, right? I could turn it so that this side is on the top, or that top side is on the right, or it's on the bottom, or it's on the left. There's 4 different ways I could turn that thing. So the angle of rotational symmetry for the square is 360 divided by 4, which is 90. And then if you want all the angles of rotational symmetry, you just take all the multiples of 90 up to 360. So 90 plus 90 more is 180. Plus 90 more than that is 270. Plus 90 more than that is 360. And that's how you get your angles of rotational symmetry. Okay, so let's talk here. What if I have an equilateral triangle? Well, if I have that triangle, I could turn it a little bit, like a little bit more than 90, and then it would still fit in the hole again. And I can turn it again, and that would work. An equilateral triangle has an order of 3, because I can turn it 3 different ways to fit through the hole. And then the angles of rotation are going to be 360 divided by 3, which is 120. And then I just add 120 to itself over and over. So 120 plus 120 is 240, plus 120 more is 360. All right, a rectangle. Now, a rectangle has 4 sides, but if I turn this rectangle 90 degrees, a quarter turn, it's not going to fit into the same hole. I got to turn it upside down for it to fit in the hole again. All right, so this rectangle has an order of 2, because I can either put it in the way I have it, or I can turn it upside down and put it in again. 2 order. So my angle of rotation is 360 divided by 2, which is 180. And all the angles of rotation would be 180. And then 180 plus 180, which is 360. All right, and then if I did a regular pentagon, meaning all the sides are the same, or a regular hexagon, then I can just say, well, a regular pentagon has 5 congruent sides that'll all fit in. A regular hexagon has 6 congruent sides. Those will fit in. And so I will do 360 divided by 5, which is 72. 360 divided by 6, which is 60. And then my angles of rotation would be 72. 72 plus 72 is 144. 144 plus 72 more is going to be 216. Plus 72 more than that is going to be 288. And then plus 72 more than that is going to be 360. And then over here I would have 60 plus 60 more, plus 60 more, plus 60 more, plus 60 more, plus 60 more. Notice all of those have an angle of rotational symmetry of 360. Everything does. Because if I take something like this marker and I turn it 90, 180, 270, 360 degrees, it looks the same as when I started. Marker with the black on top, bloop, bloop, marker with the black on top. That's called the identity transformation. When you turn something all the way around, it looks exactly the same. It's itself, it's its identity. Now, a couple of these, namely this one and this one, have 180 degree rotational symmetry. That means it looks the same right side up and upside down. Okay, and things that look the same right side up and upside down are said to have, there we go, point symmetry. Okay, so if 180 is one of your angles of rotational symmetry, then you have point symmetry. Okay, the center is the point that you could turn everything around. Okay, and if you turn it around that center 180 degrees and end up in the same place, then you got point symmetry. All right. So examples of things with point symmetry. This parallelogram has point symmetry because if I were to spin it upside down, it looks exactly the same. If I were to turn this upside down, this acute angle would map to the other acute angle. Now notice that parallelogram is a great example of something that does not have line symmetry. There is no line I can fold that on so that it lines up onto itself. And if you don't believe me, I'm going to do some math magic right in front of your eyes. Da-da-da, scissors. I am not going to run with them. Don't run with scissors. It's a bad idea. And I am going to cut out a parallelogram. Do-do-do-do-do. I'm going to make this slanty, and then I'm going to make this slanty. Ta-da! Parallelogram. If you look at this, looks like a parallelogram. I've got the really pointy end right here. If I turn it 90 degrees, nah, it doesn't look the same. But if I turn it 180 degrees, the really pointy piece is in the top corner again. And then I told you it doesn't have line symmetry. Well, that's because I can't like fold it in half and have anything line up. Like that just doesn't, no, that's not going to work. I can't fold it straight down. If I try to do that, I mean, you can kind of see this thing pokes out. What if I tried to fold it on a diagonal? Well, I mean, if I try to do that, I'm doing my best here on the desk. If I fold it on the diagonal, this part pokes down underneath. So parallelograms have point symmetry. They can be turned upside down, but they cannot be folded. They do not have line symmetry. A rectangle you can relatively obviously turn upside down and it looks the same, but a trapezoid, if I turn that upside down, the little part's on the bottom, and that's not right. And an equilateral triangle doesn't have point symmetry because if I turn it upside down, instead of having a flat bottom, it's got a pointy bottom, and that's not what I want. All right, so point symmetry is if you can turn it upside down, it still looks the same. Now, we've talked about order, which is the number of ways you can turn it, and we've talked about line symmetry. If you add up the number of lines you can draw and the number of ways you can turn it, you get what's called the total number of symmetries. Okay, so if I want the total symmetries for an equilateral triangle has 1, 2, 3 lines of symmetry, and I can turn it 3 different ways, so it has 6 total symmetries. Okay, so that are all the notes on symmetry, and now we're just going to do a couple quick examples together. Which of these objects has point symmetry? Well, let's see. Can I turn this around a point and it looks the same upside down? I think I can. That's a parallelogram. It does have point symmetry. So yes, this one works. If I turn this pentagon upside down, it's going to look like this. No, because I'll have the pointy part on the bottom. This does not have point symmetry. But this sun has a point on the top and a point on the bottom. If I turn this upside down, those points would line up. This has point symmetry. And believe it or not, that king has point symmetry. If you have a card at home, give it a shot. These cards, the face cards anyway, always have point symmetry. The number cards do not because they don't reverse the order of how why can't I think of that? The suit on the card, but in the face cards, they turn the suit upside down, and face cards do have point symmetry. All right, we got a pentagon again, using regular pentagon, A, B, C, D, E, pictured to the right. Complete the following. Construct one line of symmetry, then draw the remaining lines of symmetry. All right, when you see the word construct, that's math speak for get out your compass. So if I had to construct a line of symmetry, one of the things we learned is that lines of symmetry are perpendicular bisectors. So I'm going to make the perpendicular bisector of ED. Here's the thing. This program that I'm using right now doesn't have a compass. So I'm going to use my handy dandy hand compass to construct this line of symmetry. So I'm going to open my hand compass more than halfway, draw an arc. Then I'm going to put the pokey part on D, keeping the same compass measurement, draw an arc, and then connect the dots. There is one line of symmetry. And then it says you can draw or sketch the other lines of symmetry. So my other lines of symmetry are going to go through a vertex and be the perpendicular bisector of the opposite side. So again, remember your lines of symmetry are where you can fold it. Now, if I were better at drawing, these would all intersect at a single point. Again, don't have a ruler, using my computer. So construct a line of symmetry, draw the rest of them. Cool, I did that. There were 5 lines. I'm just going to write that down to remember. Label the center R. Okay, cool. So there's the center of rotational symmetry. How many ways can I turn it? Well, it's a pentagon. It's got 5 sides, so I can turn it 5 different ways. All right, describe all the symmetries explicitly. What kinds of symmetry are there? We have line symmetry. We have rotational symmetry. And technically speaking, we also have identity symmetry, but everything has identity symmetry, so we don't always list it. How many kinds of rotations do we have? Well, 5. I already said that. What are the angles of rotation? So to get the angles, you do 360 divided by the order, and get 72. And then you just add 72 over and over and over. So we said that was 72, 144, 216, 288, and 360. How many reflectional symmetries do we have? Well, reflectional symmetry is another fancy word for line symmetry, and we drew in 5 of those, making the total number of symmetry the 5 lines plus the 5 turns for 10 total symmetries. All right, that's kind of a long video for day 2. But here's the thing. When you're doing these, think like a 7-year-old, okay? And you will be A-okay just fine. All right, so I am done. Your task now is to find your homework packet and do the day 2 homework in your homework packet. I believe that I have it here. Your day 2 homework in the homework packet starts on page 2. I think the most fun question in this whole packet is right on this page, number 2. You are asked to shade so that when you fold this, it folds along a certain diagonal and lines up. So what you're going to do in number 2 is shade 2 of the squares so that something has a certain kind of symmetry. So this says shade so that there is one and only one vertical and horizontal line of symmetry. So if I want this to have vertical line symmetry, don't scribble. I'm doing this to show you a wrong answer. If I want vertical line symmetry, I could shade these 2 boxes and say, okay, vertical line symmetry, I could fold it, they would line up, no problem. But the question says only one vertical and only one horizontal. If I fold this horizontally, my shading isn't going to line up with other shading. So it can't be the top 2 boxes. Where can you shade 2 and only 2 boxes so you could fold it one way or the other way and those shadings would line up? That is your task. So you are going to do the homework on page 2 and page 3 and page 4, 2, 3, and 4. But again, think like a 7-year-old when you do these. Okay, I promise it will help. I am done. This has been a long enough video as it is. Have a good one.